everybody to our second lecture of this year. I'm proud to introduce today Tony Paulin from Paulin Research Group, as who is known as the original author of Caesar 2, but in the early days and now has moved on to FEA Tools for many years already. He has a few years ago introduced FEA Tools for Caesar, and this talk will be about SIFs, FEA Tools and the implications for pipe stress engineers, pipe stress in general, and now and going forward. Please give the word to Tony.
Okay, thank you, Niels. And this is for an hour, right? For 1 hour?
Yeah.
Okay. And if there's any questions as we go, please stop me and we'll try to answer them as we go. So the main points of the conversation are we're, as Neil said, talking about new SIFs and other changes in the code. So what we'll see is that there will hopefully be a segregation. So with new SIFs, we've got a new approach to pipe stress a little bit. So we'll have to segregate the critical lines into not critical lines, or into things where we can make mistakes and it's not a problem, and things where we really can't make mistakes. So there are places where it's okay to mess up and things where it's not okay to mess up. What we'll see is that the new SIFs have provided us a slightly different economy. So hopefully what we'll see is that we can eliminate waste from gross over-conservatisms that are in the pipe stress calculations we're making today. Next, we definitely want to eliminate dangerous non-conservative situations. So we'll be eliminating waste, which will be the biggest change due to the new SIFs. And then eliminating non-conservative situations will be certainly important, but the smallest change that you'll see from the new SIFs. And then at some point we'll see, hopefully we'll be observing new trends and patterns in pipe stress. And one of those will be validating models. We say right now that everybody that does pipe stress gets an A, because you do your work, you take it in, you set it down in front of a teacher who doesn't exist, and then you leave, and eventually you get an A on your report card. And nobody checks your work and nobody even looks at it. We take our pipe stress, looks okay, Caesar says it's okay, we put it in a drawer, they build it, we hope it's all right. Very few times does somebody really go back and check the results of the pipe stress. They don't check if they built it right, they don't check if the results from the analysis matches what's really in the field. It's just not validated anywhere. Very little of what we do is validated. So we'd like to think that we can be validating these things in the future, because there are a lot of things changing in pipe stress, there's a lot of things changing in the piping industry. You're being asked to do more faster, you're asked to do more with less. We're getting less quality fittings from overseas, everything is thinner. So at some point something's going to break. So we would like to fix breaks before they happen. So we'd like to validate our models, we'd like to be able to predict cracks and flaws, we'd like to know when we need to go out and inspect. So I think as pipe stress engineers, we won't just push paper anymore, but we'll be validating models with what's really going on in the plant, and then we will be able to go out and inspect and find problems and flaws that our pipe stress program suggests that they exist. So that's what we'd like to be able to do, and we'll look at the tools to hopefully do that. And as part of the conversation today is the software tools and then what's new in the American codes, which is B31J. Okay. So let me try to put things in perspective. So with the new codes, there will be a change in the stress intensification factors. So the typical change in the stress intensification factor is of the order of 2. So stresses will go up by about 2 times. So the safety factor for our piping today, once we get over about 5,000 cycles, is about 2. So the safety factor is 2 and the stress goes up 2. So what does that tell you? Well, I mean, that's an accident waiting to happen, right? Well, accidents waiting to happen in piping systems are fatigue. And fatigue failures occur when the stress is right at the allowable, or right at twice the allowable, twice the safety factor. Accidents occur at the end of life. So the problem with piping is that somebody makes a mistake, 5 years into it, 10 years into a 40-year life, you think everything's fine. Well, at 30 and 40 years, you've got an almost through-the-wall crack, or you have a through-the-wall crack, because that's what we're trying to predict. So clearly what happens is we want to predict those failures, because we don't want, at the end of the life of the system, for there to be cracks and leaks and fires and explosions. Now, some manufacturers want, at the end of their system, to have a safety factor. So you have to decide, and you have to be able to help discuss this with operating companies. What do they want at the end of their life? Do they want a safety factor at the end of their life, or do they just want to make sure they're not going to blow anything open at the end of their life? Because it's 2 completely different things. And you've got to decide what you want to go inspect for. And if you want to inspect for code compliance, then you've got a lot more work to do. Yep, so I mean, these are just some things that we want to be able to evaluate because it's going to happen. Okay, so we have a SIF error. So somebody says, well, I'm introducing the idea that there can be SIF errors to you. And as soon as the B31J document, as soon as the new code SIFs are available to you, you will see that there have been SIF errors in the calculations you're making. We've known that since 1987. We've been talking about it for years. So we know there's code errors. They will be part of the code after probably 2016. Probably 2016 B31.3 will be the first time you're getting pointed to the new B31J document. And the SIFs are going to change. So does that mean that your piping was in error, all the pipe stress you got? Well, no, because the pipes have to be in error where there's a high load that's in error also. So you have to have a SIF error, for it to be significant, you have to have the SIF error in the place where there's a high load. If the loads are low and the SIFs are off, it doesn't matter. Yeah. So you've got to have a SIF error, a high load, and you've got to have cycles greater than 3,000 or 7,000. Because below 7,000 cycles, the safety factor is greater than 2. At 7,000 cycles, the safety factor is 2, and above 7,000 cycles, the safety factor stays 2. So as long as the cycles are low, even if the SIF is off and the loads are high, you're still okay. So what we need to be able to do is we need to be able to screen the systems so we know where we might have a problem. And then once we've screened it, then we need to be able to include the new SIFs in a recalculation, a reanalysis, and then decide if we think we're going to have a problem or not. Then if we think we're going to have a problem, we need to decide if we're going to shut things down or if we're going to continue operating. Or if, as is happening in the United States, we reevaluate the life to extend it. Because if we've got a 40-year plant, we want to extend it 20 more years. If we've extended it 20 more years, we want to extend it 20 more years. Because it's very expensive to build new things now. So we extend the life of the old things. So this is a process that will help us more accurately extend the life of the old things. So once we see that we have a problem, then we need to be able to focus on inspection and improved validation, because there hasn't been any validation to date, more or less, with pipe stress analysis when it comes to what's really built and how it operates. Okay. So this is the trend. So some of these steps will involve analysis. So what I'm going to maintain is that if any of you do pipe stress analysis in this room, that through the next 5 to 10 years, your workload will go up a bunch. And it will be the kind of workload that you can't ship to somebody who doesn't have a high degree of capacity or capability in doing pipe stress, because you're going to have to be able to decide if something's going to fail or not. You're going to have to decide how critical it is. You're going to have to decide how you want to inspect it, decide what priority you need to assign to it to inspect it, because you can't inspect everything everywhere. So somebody's got to make good engineering decisions. And people that are just button pushers with pipe stress programs can't make good engineering decisions. So hopefully this will make the need for good pipe stress engineers, it will put them in more demand, because we don't want to roll the dice with our piping programs. Right now we're rolling the dice. We don't know if we have bad SIFs at high loads where we've got bad cycles. We just don't know, because nobody goes back and checks. Well, I would argue that at some point in the future we're going to have to, because we don't want to have to be lucky to avoid a disaster. You know, we've got little time bombs out in our plants that are set to go off at close to the end of life. And, you know, we can find them before that happens, and we want to be able to. Yeah. So it's an interesting question now, is this idea that I introduced to you, because you're doing pipe stress today. So the pipe stress you're doing today, if you're not using something like B31J or more applicable data in some manner which is available to you, which you probably aren't, then the question is the pipe stress work that you're doing today, is it going to have to be redone? And the answer is yeah, probably some percentage of it, absolutely. Because for some percentage of it, you're just using the wrong stress intensification factor. You're using the wrong flexibility factors. So some part of it is going to have to be redone. So at some point, hopefully what will happen in the next 6 months to 12 months is you'll start seeing more of this, and you'll have to decide when you need to step forward and say, listen, we can't use the old technique with this before. Or a year ago, before the plant was built, we did an analysis that was really not incomplete, but the code has augmented these calculations now. So we need to make a better analysis of this to know if we should install it this way. Yeah. So I mean, this is, we can't follow the crowd anymore. You know, it used to be, as Caesar says it's so, it's so. If the code says it's so, it's so. You know, well, now the code is going to have a different story. The code is never retroactive. Like B31.3 will never tell you you have to go back and redo the calculations. but common sense and morality and an ethical nature tells you that, yeah, gee, for some of these systems you might have to. Yeah. Okay. Clearly there's some legal implications, because at some point, if one of these little time bombs goes off and somebody gets hurt, somebody's going to come back and follow the record back and say, who did the analysis? And at what point did they know that this time bomb could have gone off, and did they do anything about it? And so there's a little bit of a legal involvement here. And then of course at some point we want to be updating our technology, because now with the existing codes we're using technology from the 50s and 60s. You know, we want to at least be driving an old beat up station wagon, because now it's still horse and buggy. Okay. And last but not least, this is probably the most important thing, and I'll show you some diagrams. The most significant implication of the new SIFs is that we've been burning money for years. People say, so what, it's conservative. But if you're 5 times conservative or 10 times conservative, and the desire is to be 2 times conservative, we're burning money. We're literally burning money, because we're rerouting pipe we don't have to. So when the D over D ratio is much less than 1, and when we use 0.75I as the sustained or occasional stress multiplier for branch connections, we're over-designing, grossly over-designing piping systems. And the new Appendix D and B31J will give us ideas and will give us the quantitatively how far over the allowables we are in terms of, was it 6 times, 8 times, 11 times? Yeah. So hopefully we'll be able to stop being so over-conservative. We won't have to reroute as much. The pipe stress work will come in and go out, because we won't be rerouting lines. We won't think things are overstressed. We won't be moving supports around that we don't need to. This is supposedly the biggest implication. So it's an economically smart thing to do, which will have a positive effect on pipe stress. Okay, so let's talk about B31J. The title of B31J, and this is a new title, they've been tweaking it: stress intensification factors, flexibility factors, and their determination. So what B31J was prior to this, I mean, it's an existing document now. B31J is how to do the SIF calculation, not the SIF test. It is a SIF test standard. But now what it is it's a SIF test standard. It's a K-factor test standard, because now we have K-factors in the code for branch connections, and it's a sustained load test procedure. And it has stress intensification factors and flexibility factors for common metallic piping components. The idea is that B31J will replace Appendix D in B31.1, B31.3, 4, 5, 8, and so forth, and also be referenced in Section 3, because Section 3 doesn't have a sustained or occasional, they call it primary load test procedure today for B2. They don't have it. They've been working on it for years. The code says to be developed. There's no work been done on it. So B31J is the only code document in the world that we know of now that gives you a procedure for determining what 0.75I should be for your sustained and occasional load analysis. So I think you'll be able to go in, I think that's important. So I think you'll be able to go in, look at the document and say, I want to run a finite element calculation. This tells me how to do that. I want to run a test. This tells me how to do that. So you know exactly what to do to get the right stress intensification factors to use in the code, so that you maintain a reasonable safety factor, not something gross. And I'm going to argue that today, for sustained stresses in particular, it's very difficult to run finite element analysis and get results and even tests, because there's really not any guidance. And there's not any safety factor guidance. And we can talk about that to whatever level of detail you like. But this is all a part of the new code. There's, from the presentation we gave last year, the presentation this year, there's some updated notes for socket welds. All the socket weld guidance in the code today is for standard wall pipe, a fairly small diameter with standard wall thicknesses. The socket weld guidance in the code today was never intended for thin pipe, never intended for 20-inch diameter pipe. And the Navy in the United States is using it for both today. Well, they've run tests, so we're including the test guidance in for socket welded systems for any of you if you are using them in larger diameters or thinner walls. So there will be more guidance for that. Basic B31J updates now. The first ballot has already gone through. There were 9 approvals, 6 disapprovals. The 6 disapprovals, the biggest disapproval was that it was too big. it took too long to read, and they didn't think the code books would accept a document that took too much time to read. So they wanted it to be smaller. Okay, so we went back, we took examples out, we took words out, so we reduced it from 77 to 52 pages. SIFs and Ks were moved from an appendix into the main body of the document. Examples were taken out. And we, for those of you that are familiar with B31.3, you know that in 2010, it introduced the Sustained Stress Index, capital I. Everybody knows, right? Sort of, yeah. So there was a new capital I, but there was no definition of it anywhere. So it was introduced into the code and there was no definition. So they, okay, well, as we were writing this document, they said, would you please put a definition of this term in the B31J? So we did. So there was a B31.3 capital I definition in B31J. Well, the committee members, when they looked at it, they said, that's only for B31.3. It's not for 1, it's not for 4, it's not for 5, it's not for 8. We disagree with that. So they voted that down. So we took out the sustained stress index. So that definition isn't in there anymore at all. And we replaced it with 0.75i. So what's in there now is it says if you're doing a sustained stress analysis and you've got the term 0.75i in your equation, take 0.75i out and replace it with this. And we give you the new term for it. So you don't see SSI, but you see a replacement for 0.75i. So that's the sustained load guidance now. And everybody's happy with that, because all the code books can use it, and B31.3 can use it also. Because B31.3 says in lieu of I, use 0.75i, okay, for a sustained load. So those are the biggest changes. So that is being reballoted this coming week. So we've done all the work, we've gone to all the people that were opposed to it. They've all said, yes, we like the new revision, so now it will be reballoted again. So hopefully, changes that were made for John, Bill will agree with, and everybody will like, and it will get out of the committee. And then it goes through one more committee, it goes through an executive committee. Once it passes the executive committee, it's a valid code document. And people will start referencing it for all the different book groups. So the first book group that will reference it is B31.3. The thing I would like to point out to you in this, because this caused some confusion in the code committee, is the definition of the K-factor. So this is the first time there have been K-factors for branch connections. The K-factors that are defined are for the run and for the branch. For the run, when the D over D ratio is 1 and the D over T ratio is high, the torsional flexibility for the run can be a significant number. What happens is if you've got pump manifolds where you've got multiple inlets to a large manifold that comes in, the manifold is very soft in torsion because of all the holes that are cut in. Well, we never see that today. But this flexibility factor in the torsional direction helps you with that. It gives you the flexibility property. Okay. So these are the K-factors that are defined, and this is how they're used. They're used in general together, not separately. And that has never happened before in the piping world. So what happened is people made the mistake of thinking, oh, well, I put the branch K here, and I put the run K here, and everybody's happy. But that's not quite the way it works. So what happens is because all of these are in series, you've got to make some adjustments to the calculations. And so you'll see in the document there's an appendix that tells you how to make this adjustment. But I caution you because what's going to happen at first is FEA Tools has these calculations in it automatically. So those go into Caesar on, you don't have to do anything. But if you're running another pipe stress program or you want to check what's done with FEA Tools, you're going to have to sit down, pull out the code, type the equations into an Excel spreadsheet, determine the K-factor, then look at it, then compare it to what's in the program and say, yes, I agree. Or if you're using AutoPipe or K-pipe or something else, you're going to have to put it in those programs manually. So this is the model that you have to use for the branch connections, to use the K-factors that are produced in the code. You can't just take them and throw them in. So there's a little bit of adjustment. So I point that out so that you're aware of it. The code, of course, was written originally. This is note 11 in B31.3 Appendix D today. It says the out-of-plane SIF for reduced branch connections when the D over D ratio is between 0.5 and 1 may be non-conservative. So it tells you what you're doing today is non-conservative. Selection of the appropriate SIF is the designer's responsibility. It's yours. So they're putting all the responsibility on the designer, not Caesar, not COA, not us, not me, not the code committee guys. It's all on you. So this is the reason that B31J needs to get into the code documents. So there's a variety of SIF issues. The biggest one for non-conservative, or for over-conservatism is the D over D ratio in the SIF when the D over D ratio is small. When the D over D is small for the run size, we're using the SIF as if it's size on size. So when you've got a large D over T branch connection, the SIF for the run might be 8 or 9. So what happens is you're using 8 or 9 as the stress intensification factor instead of a value of 1. Because with a little D over D, there is no stress intensification factor in the run. But that was the conservative assumption Markle made in the 50s. They've continued to use it today, and no correction's been made. So that's the biggest, that's when we talk about gross over-conservatisms. This is one of the largest. You'll see big changes in the high D over T range because there just hasn't been any test data there. That's for, this one is for T over T between 0 and 1. This is when the T over T ratio is greater than 1, when the branch thickness is greater than the run thickness. What you see here is there haven't been any test data. So if you've got long weld necks, HB, barreled fittings, any of those things in a piping system that's large, there have been 0 tests for those. And so there's a conservatism that should be added that is being added now for new SIFs. We're not just extrapolating up and assuming, well, we don't have any data, just extrapolate up. We're not doing that anymore. You know, we run finite element calculations exhaustively and a few tests now in this range. The ASME has approved about $150,000 for testing for the new year. So we'll be running some tests into this range starting next year. So in the old version of Caesar, there's the in-plane and out-of-plane SIFs. Now there's in-plane, out-of-plane torsion axial. There will be pressure at some point in the future. Then here's where the capital I's go. So here's where 0.75 I goes. You don't have to make any change to your Caesar model because you always leave this blank. Now what happens is there will be numbers that you haven't seen before that go into these spaces. If you run FEA Tools, these are all filled in for you. Yeah. So it's, if you're running Caesar now, there's a difference, and you just don't see it because you just let it go. But there's a lot of additional numbers created. Well, with FEA Tools and other things, you'll see those numbers. The new B31J's got more pictures because people were confused with the way what SIFs applied to which fittings. Well, now we drew more pictures, so it's clear that for unreinforced fabricated tees, for long weld necks, you can simulate those. For sit-ons, you can simulate them. For set-ins, you can simulate them. OLETs, you can have straight through bores, or you can have tapered bores. So there's a variety of different OLET types because OLETs have different shapes, which is a problem that we'll talk about in a little bit. There's 2 different shapes for contoured welded in set-in fittings. So all of these are valid, and everything is referenced by a number, just like the European code does. So you don't have to call out these obscure names, you call out sketch 2.6. So 2.6 is an OLET, so everybody knows that now. So you don't have to guess at names. An OLET, weld OLET is a trademark name of Bonnie Forge. So if Bonnie Forge gets mean and they can stop you from using that name, well, sketch 2.6, nobody can stop you from using that. The form of the equations is essentially the same for bends and T's. It's just reformatted a little bit so that we could get more SIFs and K's in the same space. Here's a discussion. So this is the title for the K factor. So you can generate K factors for all the branch connections with a single test now. Before you needed to have one test, one K factor result from one test. Now you get all 5 from just a single test. So the new tests are intended to be more economical. There's the sustained stress index test. Well, I mentioned that before. This is the old title. You don't see sustained stress index anymore. Now it's sustained load. You don't see SSI anymore in the code at all. This is what the T equations look like now for Appendix D. So now what you have is you have run flexibility factors, you have branch flexibility factors, in plane, out of plane, and torsional, and you have SIFs for the run and SIFs for the branch, in plane, out of plane, and torsional. Before you had one equation, 0.9 over h to the 2/3. Now you've got 6 equations for SIFs and 6 equations for K factors. There's for saddles, there's for unreinforced fabricated T's. Before, with the effective section modulus, the effective section modulus was the same as multiplying by T over T, thickness of the branch over thickness of the run. That was way non-conservative for certain applications. As we got big pipe, the T over T ratios got less than 1, and that was just wrong. That was dropping the SIFs by too much. So now we put borders or boundaries on the T over T value. T over T value can't be less than 1 in certain cases. It can't be less than 0.85 in other cases. So SIFs, as they dropped in your Caesar calculations today, they're not going to do that in the future. There's the welding T's. There's the outlets. Okay, there's a lot of notes. Reading the notes is important. Of course, what happens is anybody that implements this will read all these notes and apply it for you. So for FEA Tools, all these notes are already applied. When Caesar puts these things in, all these notes will be already applied. But when you're checking them by hand, it's very important to go through these equations because they do control what happens. For example, when the T over T ratio falls in a certain range, now what you do is instead of using the T over T factor, you use this expression. Okay, so you just have to know that. So you have to read the note to recognize that because there's a hump in the T over T curve in terms of the stress intensification factor. The bend flexibility coefficient was wrong for 90s. We've been using it for years, 1.65 over H. 1.65 over H is for 180-degree return bends. It's not for 90s. 1.3 over H is for 90s, 1.1 over H is for 45s. But the B31.1, B31.3 folks never wanted to put that in. So we said, well, we think we should probably fix that. So they said, well, we're not changing the code equations for bends, but you can put it in as a note. So there's a note that says when you've got 90s, use 1.3 over H instead of 1.65 over H for the flexibility coefficients, because it's wrong. So what will happen is all of your bends now will get about 20% stiffer. But your bends are off anyway, and that's not something we even had time to change. The effective section modulus that's used in the code won't be used anymore. So you've got to make sure that when you take a new I factor, you don't use it with any calculation that's going to use Z sub E. All Z sub E did was include a factor T over T times the stress intensification factor. When you look at the stress intensification factors today, you'll see a T over T a term in those equations. And that means do not use the effective section modulus. So what guys are doing now in the code is they're showing where it came from, and they're coming up with a conclusion, which is do not use, well, abandon Z sub E. So don't use the effective section modulus anymore when you implement B31J or any new SIF equations, because all the new SIF equations have the term T over T in it. We resolved the issue with the Markle equation. Everybody knew the Markle equation was off. Markle, back in the 1950s when he did his test, for a variety of reasons, he developed a curve whose slope was too shallow. So what happened is in the low cycle end, Markle's curve, this one, is too low. In the high cycle end, it's too high. So the problem with that is as soon as you get over 200,000 cycles, you're very over-conservative in your, under-conservative in your stress calculation. Markle's predicting a fatigue life you don't have. So you absolutely positively shouldn't use the existing code equations above 200,000 cycles. So what do? Well, B31.3 is circulating appendix W. So what you'll hopefully see in 2016 in B31.3 is an appendix W for high cycle fatigue. And it uses the welded fatigue curve from section 8, division 2, part 5. So anyway, so there is a resolution in B31J for the differences between these curves. So that piece of information is talked about. And this is just another representation of that. Here's the Markle curve. This is the Hinnett curve, or it's called the Hinnett curve. The guy was Chris Hinnett. He worked at our company and did a whole series of fatigue tests to show the Markle tests were wrong. And then this is E epsilon. So as it turns out, E epsilon is actually higher than the fatigue curve that we're using. So the fatigue curves that we're using have a strain concentration factor already a part of them because they're cantilever tests. What that says to you is if any of you are college professors and you want to go out and do really, really accurate fatigue tests of girth butt welds, and you decide you want to use the college professor approach, which is 4-point bending, which is a really good, very dependable bending mechanism, bending test, is you can't use that. You can't use it for a piping code because 4-point bending is going to give you this as a fatigue life. When if you run a cantilever test, you'll get this as a fatigue life because cantilevers have strain concentration factors in them when the strain range gets above 2 SY. So be very, I say that because just to be very careful taking somebody's fatigue test data and then just throwing it into a pipe stress program. There have been enough mistakes made in the last 20 years when people try to do that. Another function or factor that's involved with sustained load testing that we're trying to bring out that people have made very significant mistakes in is piping survives earthquake, it survives water hammer, and it survives errant calculations because it's ductile. The seismic loads that we're using are way underestimated for real seismic events. The reason that buildings stay alive and the reason that piping stays up in true seismic events is because it's ductile. It bends a bunch at the elbows. The loads are much higher than what we calculate in any pipe stress program we run today. So we have to make sure everything we put in a piping system is ductile. What's not ductile? Junctions, where we put clamps. Some clamps in large diameter pipe aren't ductile. Some explosion bonded fittings aren't ductile. Those things are designed so that you can put fancy stuff on one side to fancy stuff on the other. You can weld stainless to aluminum. So you can do things you couldn't do otherwise. There are ways to hold pipe together so that it's flexible. Those things, the manufacturers all want SIFs of 1. So if they give you SIFs of 1 because they know they don't have a fatigue component, the problem today is in the code you're using 0.75 times I for your sustain load. And they are pressure sensitive to external loads. So when you put the design pressure on them, they won't carry the design load for straight pipe. If you put the design pressure on them and then put the load on it, the bending moment on it, that straight pipe will carry, they rupture. They are pressure sensitive. You know, their sustained load capacity is not a function of the capital I or the little I factor. You know, when you put pressure on, they break. So there's new test procedures in B31J that identifies pressure-sensitive sustained load components. And they are predominantly clamps, they're predominantly ball joints, they're predominantly explosion-bonded fittings, you know, anything that's fancy that holds stuff together. Yeah. So if you've got manufacturers that say, well, the SIF is 1, code says 0.75I, so use that also in the sustained stress analysis, I would urge you to go back and read through some of these paragraphs and then ask the manufacturer, have you done this? Are you pressure sensitive? And if he says yes, then there's mechanisms for safeguarding. And you got to think, what do? If you get something that's pressure sensitive, what you do is you make sure it doesn't suffer bending, right? Because the problem in earthquake is that things shake a lot. Well, at high points where it's high bending, that's where it plastically deforms. So you don't let these things get exposed to high sustained bending moments. So you put them in a straight piece of pipe, but supports all over the place. No problem. Yeah. So that's the safeguard recommendation, hopefully. Well, that's what it is. Whether the words come out that well or not, I don't know. Okay. What people did, so we're at, we've got 30 more minutes? So what people started doing is once B31J was, folks have started evaluating it. So what somebody did is they started with 36-inch standard wall pipes, so 36 by 36 down to 2 by 2s, all standard wall. And they looked at the existing calculations and the new calculations. And what they said is that you've got far fewer 36-inch Ts than you have 2 by 2-inch Ts. But the 36-inch T is a lot more expensive. So what happens is the 2-inch Ts and the 36-inch Ts have the same physical weight. They are weighted the same through the distribution for economic evaluation of piping. Okay? So if you agree with that, I mean, so that's the assumption. We just had to make an assumption. So that's the assumption. You don't have anywhere near as many of these as you have of these, but these are more expensive than you have by quantity of these. So we say they're about the same. Okay, so that's the assumption. So then the issue became, is what's the distribution? So this is the distribution of overly conservative in terms of what we're doing today and not conservative enough. So the total integration of the volume of or the area of the blocks is how much is overly conservative. So most of it is here, so most of it, what we're doing is okay. Here's the overly conservative things. So the overly conservative is the total area of these blocks compared to the whole area of piping. So you can see there's a lot more over-conservatism than there is under-conservatism. The under-conservatism maximum magnitude is 3. So under-conservatism for the existing SIFs, we're off by about 3 times. Over-conservatism is 11. So we're 11 times over-conservatism. And we've got more stuff that's over-conservative than we have under-conservative. So that's why we're saying that when we implement the new B31J, what's going to happen is piping system cost to design is going to come down. That's the hope. I mean, it's going to be a more economical piping system that we build. So it's a code change that we think is going to be accommodated. Okay, so what happens? So we know that some of the SIFs are off. So now we have to do what we were talking about in the beginning. is we have to screen piping systems. So we have to take essentially all the piping systems that we've ever analyzed, right? Because those are the ones that could have problems, and we need to be able to screen them quickly. And where there's perhaps a problem, then we need to pull it off to the side and say, okay, do we need to analyze that? So if I'm a shell, or if I'm somebody that's, I don't want to hear that I've got a little time bomb in my plant that might go off at the end of the design line. You know, I just don't want to know that. But if the SIFs are off and the safety factors too, and the SIFs off by the safety factor, I mean, you don't have to be a genius to do the math on that, right? So what do initial surveys suggest? So there have been a lot of initial surveys done. This is not a scientific evaluation by any stretch of the imagination, but I would tell you that this is what we've seen as we've gone through many hundreds of models, that 5% of 5% of the lines that are analyzed would numerically result in through-wall cracks at the end of life. So 0.25% of the piping systems that are out there would suffer potentially a through-wall crack at the end of their life. Now, when you think about it, a through-wall crack means that 50% do and 50% don't. So this is just that would suffer a through-wall crack. So 0.25% hit that 50% mark. So 50% of those are going to be safe. 50% of those aren't. 50% of those, some percentage of those are going to fail sooner. So what that says is 5% of the lines that are screened would not pass screening, because we'd want to take all of our lines and screen them, because you sure don't want to have to reanalyze everything. So 5% of what you screen doesn't pass. Then you have to analyze that. And 5% of what you analyze is a problem. And then what you have to do is you have to decide whether you want to, well, basically what you got to start inspecting. And you got to decide when to start inspecting. Because if you recognize this problem after 10 years and you're not going to have a crack that you can probability-wise find until after 20 years, it's a waste of time to inspect. What you do when you do the calculations, you say, Mr. Operating Company Owner, in 10 more years, you need to go inspect this point at the next downturn. You take the insulation off, build the scaffolding, and go out, and here is the prescribed inspection procedure you should use. And it'll be some sort of phased array more than likely, because that's the most sensitive volumetric inspection that we can have that requires the least amount of technology. Now, in 10 years, it'll probably be different, but that is the way it is today. So we're writing specs for phased array inspection today. And the interesting thing is you will find a damaged material with phased array that you can't see with fluorescent particle inspection or fluorescent penetrant or even regular penetrant inspection. Yeah, so penetrant inspections don't find a flaw where phased array sees big red. So you can validate that, yeah, this is a place that's been overstressed. Okay, so we're interested in that. We're also interested if the user comes back, because you never know what an owner-operator is going to ask you. You never know what an insurance company is going to ask you. So 15% and 10% don't satisfy the code. So 5% of 5% is potentially not safe. 15% and 10% won't satisfy the code. So what that says is that if you screen to pass the code, then 10% of the systems aren't going to pass that screening procedure. Because what happens is, if you're really going to have a failure, you really have to have cycles. If you don't have cycles, you can still fail the code, because the code says you will design for a minimum of 7,000 cycles. So what happens is you're going to have more that jump out of screening. If somebody tells you, I want to make sure that we don't have anything that invalidates the code. So you're going to have to talk to the operating company, right, or the insurance company, and say, listen, if you want me to make sure you've got code acceptance for everything, that means a safety factor at the end of life, we're going to be doing a lot more pipe stress analysis. And then he just needs to decide if that's money he wants to spend or not. Okay, so let's summarize. So 5% of 5% is for through-wall cracks, 15 to 10% is for having a code safety factor at the end of life, because that's what code compliance means. Not that it fails, but that you've got the intended safety factor at the end of life. Yeah. And I think it's important to differentiate that, because some people think that if you're over the code, you're going to fail. And of course, that's just not the case. So let's just look at some numbers. 5% of 5% is 0.25%. 20 out of 400 will not pass screening. So if you take 400 lines and you screen them, screening takes maybe 5 minutes, maybe 10 minutes. So you screen. 20 out of 400 need to do more analysis, because it's got a high D over T ratio. It's got an OLED on it between D over D of 0.5 and 1. It's got cycles greater than 5,000. It's got blah, blah, blah. It's got just a variety of things where we know the SIFs are wrong. So then 1 out of the 20 will have a problem. So if you start with 400 ISOs and you're at an average piping system, what's going to happen is one of those is a little time bomb that's going to cause a problem or have a 50% chance of failing at the end of life, through a wall crack at the end of life. So not very many. But is 1 out of 400 too many? I mean, somebody's just got to answer that question. Okay, so 15 to 10%, so 40 out of 400, if you're looking for code compliance, will fall out of screening, because the screening doesn't involve cycling anymore. So you have to, so more will come out that you have to analyze if you're interested in code compliance, and then more of those are going to jump over non-compliant code rules, because you need more of a safety factor at the end of life. So about 6 of the 40 will have to be looked at the end of life because they won't be satisfying the code. So not very many. And you just have to decide if that's important or not. Interestingly enough, the biggest reason to use the new code is because it's going to save you money. It's going to require less rework. You're not using gross over-conservatism. That's probably the biggest reason, because there's just not that many things that are that we're off, but okay, we're off. So, okay, clearly depending on type of plant, size of piping, pipe stress, velocity, fluid medium, design constraint, material, etc. You know, what I gave you was based on an average. I mean, there's certain things that are going to make those percentages higher or lower. So don't take that as gospel, but that's the closest thing to gospel you're going to find today, because we're the folks that, I mean, we're not very smart necessarily, but we just have lots of piping systems. People have sent us lots of piping systems. So we've just evaluated a bunch. So I can give you some idea of what we've seen. So this is the ratio for over-design. So 10% to 20% are over-designed. So what that means is that so 20% of the line screen won't satisfy the criteria for over-design. The criteria for over-design is that the stresses, you think the stresses are twice as high as they really are. So that's just a crude definition of over-design. So 80 out of the 400 lines will screen for over-design, and 8 of the 80 will show that you're using stresses or think you've got a stress that's twice as high as what you really have. So that's about the percentage distribution that we think is going to occur due to over-design rules. Okay. What's the screening criteria look like? This is a basic screening criteria right now. It's in FEA Tools. If you don't pass this, then you jump into a second screening criteria that's more detailed. And if you don't pass that criteria, then it says you need to start doing some calculations to validate. So the things it asks for, D over T ratios, D over D ratios, number of pressure cycles, number of thermal cycles. Is it carbon steel? Do you have a D over D ratio about 0.7? Because that's where the SIFs are off the most. If you have an OLET, OLETs can be terrible. So these are just the questions that we ask to help you go through the screening process. So once you go through the screening process for a whole series of lines, you get a table, and then it comes down and it shows you which lines need to be prioritized for doing analysis. Start doing the analysis. If you find that none of them require any extra work, then you say, shucks, you know, this is really good, no problem. We've checked this system out. And you can tell the owner that even though there's new SIFs, even though there's new approaches, what was done in the past for your system is just not a problem. And he can breathe easier. Okay, FEA Tools helps the user do this. The new version of Caesar is linked with the new version of FEA Tools. So from the Caesar menu, you can go straight into FEA Tools. From FEA Tools, you can pull in all of the models in your directory. So if you want to pull in all the models from your directory and ask for all of them to be translated and all of them to be compared, it will do that automatically for you. You don't have to do it one at a time. So what we're trying to do is make this comparison process easy if you've got all the old Caesar runs. That's the idea, is having the old Caesar runs. So there's a whole new set of comparison tools. There's a whole new set of capability in this version. If you've got systems where you think you've got a problem, then we don't want to use gross over conservatisms that are even in the existing code. People say, well, B31J, that's the latest, greatest, that's the state of the art, right? I mean, that's the best. Well, I mean, it's the best as of 7 years ago. Okay, that's when it was finished. So over the last 7 years, we've been running a variety of tests. We've been looking at other things. We've been looking at bends. Nobody wanted bends redone much in the old code. Now we've looked at all the problems for bends. So there's a whole lot of new things. So For example, if you're running stainless steel or zirconium or titanium, the pipe is very thin. When you weld it, the weld can be thicker than the pipe wall. Well, that's not considered in the code equation. So if you've got stainless, zirconium, or titanium, you're using a very, very thin weld when you've really got a bigger one. Bigger welds reduce the stress intensification factor, and they reduce the flexibility factor. Well, with the new version of FEA Tools, you can put the weld size in. If you want to grind a weld, if you want to volumetrically inspect it, that's better than what the code requests. So you can reduce the stress concentration factors by a known amount by doing this inspection. So all those things are available to you if you want to go in and do a little bit more to reduce the stress some, to not have to do something else later. So you can do a better analysis, hopefully, with the tools as they're set up, because we know there's going to be some problems. So you can specify your own SIFs, no big deal. You can put in I's and K's for a variety of things. 661 header boxes, where we've got rectangular header boxes. There's been no real good guidance for flexibilities of those. Those things can be incredibly flexible in one direction. So what we did is we put in, there's a finite element program now that calculates the K factors and I factors for those and puts them back in the Caesar model automatically for you. There's a vessel head and vessel cylinder calculator for you. So if you want to make a finite element calculation of a hillside nozzle with a pad reinforcement on it, that calculation will be made automatically, and the SIFs flexibility is put back in the Caesar model. And then that can compare to the old Caesar model. For bends, the biggest issue with bends today is that the code SIFs for bends assume matching pipe, matching bend, matching pipe. There's no difference in the thickness of the bend. And they've got one adjustment for the length of the attached pipe. It's either 0 or it's infinite. And those are the two controls. What happens is the biggest thing that affects SIFs and Ks and bends is the amount of attached pipe. If the amount of attached pipe is less than this number, then the I's go down and the K's go down by some amount, and it's that number on both sides. So what happens in general in piping systems, you don't have these links, because as the D over T gets bigger, this number gets really big. So you don't have these links, so you don't have the I's and the K's. You've got a different K factor for each bend, which Caesar really doesn't give you much of today. And you've got a bigger bend than you have attached pipe, because the bends are made thicker. So none of those things are considered. Okay, well, what FEA Tools does, this is something that we've been working on for 10 years. Right, there's a PhD at the office that's been working on that problem for about 10 years off and on. So we finally think we've got the problem solved. So now there is a beam element in FEA Tools that takes the Caesar beam model, replicates it locally, generates the I's and the K's that should be put back in the software, and puts those back in for every bend in the model. When's that important? Rotating equipment. Yeah, rotating equipment type piping systems, where getting the flexibility and the loads right is important. If you've got a short amount of pipe, if you've got short loops, short closed loops, those are tight piping systems, and they're very, very, very sensitive to the actual values of the stiffnesses you use. A K is different now for every bend. So you turn that on, turn it off for FEA Tools, and see what effect it has on your model. That's just reality. I mean, it is just reality. The worst bends that we see are short radius bends. If you've got D over T greater than 40 and a short radius bend, code equation right now is just not very good. It just wasn't intended for that. The code equation now was developed back in 1904, and it assumes that you've got uniform ovalization all along the bend arc. So you've got uniform ovalization up to the straight pipe, and all the straight pipe is ovalized through about this length. Well, that's just not what happens all the time, right? Existing code equations for 160 or 180 degree return bends. The K factors, as we talked about, go down as you get to 45s. So if you've got a whole lot of 45s in a short system, what you're putting in is just completely off base. There's no reason for that. We can correct that. Yeah. So FEA Tools corrects that automatically. So bends are one of the things that we've corrected. Why don't you put that in the codes? We couldn't get the K factors in right. We had to put the K factor for 90 degrees in a note just to change, because they wouldn't let us change the existing bend equation. Could you imagine trying to put in expressions for these things? You know, I mean, it's, okay, someday that'll happen, but today it hasn't happened today. Okay, so FEA Tools let you put in all the additional bend data. You can put in the attached leg lengths. If it goes out and pulls them in from Caesar, if you want to change it because you don't like the number, you can put in the changed bend thicknesses. You can put in different thicknesses for the intradose and extradose. If you've got a tapered bend, you can put in a tapered bend. So all of those things can be put in, and then the model will be replicated for you in Caesar. So it's trying to make the calculation better. Probably not this version, but the next version will have refractory in for the bends, because refractory drives the K-factor to almost nothing. So it's very typical for a large diameter refractory line pipe to have elbows to have K-factors of 40 and real K-factors of 4. And you just don't get that in Caesar today. You don't get that with the, what is it, the Charthy? What's the word? Who's the guy that did it? Sharpie? Is it Sharpie? That's a Sharpie? Well, it's yeah, something like, it's got a P and a Y and a CH and an A somewhere in the middle. But, so he developed an expression for including the refractory and stiffness calculations. But that's for longitudinal stresses. It's not for bends where the flexibility comes from ovalization. You know, the flexibility of or the refractory, thick refractory affects the ovalization a lot more than it affects local bending and straightening. So anyway, so that will be in FEA Tools. Probably not this version, but the next. So that plus external rings. Because when you have large bends, you start putting external rings on the pipe, in case you've got that. Okay, so we talked about that. There's a ton of comparison tools. So you pull all these things in, you can pull all the models in and look at them at one time. You can compare them all to each other at one time. So there's just a variety of things you can do to see if there's differences. Because what we're trying to do is let you do screening of all these piping systems over again, very quickly. The nice thing is if you can screen quickly, you can also do your stress analysis quickly. Yeah. What makes it able for you to run a whole lot of calculations real quickly, also lets you do a lot of new design quickly. So the hope is that all of this stuff together will improve what you do with pipe stress. Okay, these are just charts and plots. And of course the other thing is FEA Tools also helps you when you've got overstress conditions, because you're including proper flexibilities, and most of the SIFs that you put in are going to be lower rather than higher. And so you won't see as much red just by default. Okay, 20 more minutes? I mean, what, 15? Okay. The last time I was here, I talked about margin consistent loads, because everybody wanted margin consistent loads. That was the theoretician's dream for sustained stress analysis. So what happened is we found some personal communication between some of these guys that the nuclear guys looked at it and said, margin consistent, the sustained loads don't work. So what happened was people were producing margin consistent loads for sustained stress analysis, and then people were rejecting the calculations. People were running finite element calculations and saying, well, I'm doing a finite element calculation for my sustained stress, or my occasional stress, so I want to be conservative, so I use elastic perfectly plastic, so I leave out large rotation, so I don't put in large strain. That's conservative. And then they would compare it to the B2 values from section 3, or to 0.75i, and say, wow, these numbers are terrible. Well, the problem is when you do a nonlinear finite element calculation, and you include a conservatism like elastic perfectly plastic, no strain hardening, or like lack of large rotation, whereas it starts to deform, it doesn't get harder or stronger because it's like a guitar string. When you leave those out, you're including a safety factor whose value you don't know. So when you include that safety factor, you can't take those results and compare them to anything else. And that was the problem. Guys were running these conservative finite element analyses for large parameter ranges of problems, and then comparing them to the existing calculations and saying the existing calculations are wrong. Okay, so that's the nature of the problem. So if you're running ANSYS or Nastran or whatever, make sure if you're running a nonlinear analysis that you know what you're comparing to. So we won't go into detail because we only have 10 minutes. If we had 15 minutes, we could go into detail, but we don't. So if that comes up, then I would recommend that you talk to Dynaflow, and they can help you.
Yeah, until 6, huh?
Well, you're kind. So anyway, as you know, all you have to know is hear it, right? I mean, just so you wouldn't make that mistake. You wouldn't make that mistake. So what happens? Let me show you the conclusion. So the conclusion is this is what's showing up in B31J. So B31J says whenever the factor 0.75i used to say capital I, and B31.1 didn't like it, and 5 didn't like it. So now it says whenever the factor 0.75i is used in the B31 code evaluation of sustained or occasional loading, it may be replaced by the factor 4/3 SYZ over M2. M2 is the twice elastic slope load. So that's the collapse load, defined by the twice elastic slope expression. Now, can you replicate that in a finite element calculation? Absolutely. Put in an accurate material curve, multilinear material curve, put in large rotation. Twice elastic slope it doesn't generate enough strain to require large strain, so it's a relatively simple finite element calculation. Use a Ricks method or an arc length method, make sure you do that, otherwise it'll diverge too quickly. And then plug M2 in there, take S, Y, and Z, and you've got a better calculation for 0.75i. Because 0.75i now for branch connections is way too high. So the new calculations will give you much better values for 0.75i. 0.75i is good for nuclear type components where everything's really thick. It's terrible for anything where the D over T ratio is greater than 30. Because where the D over T ratio is greater than 30 to branch connection, it's a local bending stress that causes the fatigue crack. Local bending stresses have nothing to do with collapse. So it's just a very, very poor correlation. So this gives you much, much, much lower sustained stress indices, or 0.75i values. So if you're running a pipeline or something, and somebody's got an intersection and a whole bunch of pipe in the vertical direction, and the designer didn't put any supports in it, now you need a ton of supports. In reality, you don't need supports at all. You know, so you don't have to put steel in, you don't have to reroute the pipe, you don't have to route the pipe over to steel. You know, I mean, hopefully this will be economically effective for you. I don't think anybody in here does nuclear. This is the sense, this is what happened to the nuclear code equation, and this is why everything was confusing. The B31.3 code uses, by default, consistent sustained stress indices. A straight pipe fails, if you take the allowable and double it, that's when straight pipe's going to fail. So you get the allowable from M over Z equals 2/3 SY or SH. That's your allowable moments developed from that equation. So if you take straight pipe and put the moment that's double the allowable on it, it's going to collapse. If you take an elbow and put double the moment on it, it's going to collapse. And that's the way the B31.3 code is set up. That's not the way the nuclear code is set up. The nuclear code is set up so that they've got different multipliers on different components. And what happened, and this is what confused everybody, is everybody was using consistent results. They said, we want bends to collapse the same time as straight pipe. Nuclear code doesn't. The nuclear code lets straight pipe collapse at a higher level. So you only have to go maybe 20%. So the nuclear code lets you use 80% of the collapse load for straight pipe, but only 50% for everything else. So that's the difference. So the nuclear code, with the nuclear code equation for B2, there was never before a test for B2. This is the test for B2. There's these phi values. So 0.5 for curved pipe, 0.5 for everything else, but 0.78 for straight pipe. So that will give you the quote-unquote consistency. But the nuclear code doesn't want it, right? I mean, so the nuclear code uses these, so you can put you can take straight pipe closer to collapse. Well, that's what they want, that's what they've been using, so, okay. And this is, you know, we've done a whole bunch of tests to try to validate that. This is the existing code. Existing B31.3 code gives you an allowable load that's greater than the collapse moment. So clearly things like that need to be fixed. These are the tests we're running in Houston. Yeah, okay, this not important, this not important. Here's the twice elastic slope load. Here's the definition of where the safety factor is in twice elastic slope load. So there's a twice elastic slope load that's based on test and finite element calculation. It's pretty straightforward. This is the allowable. For B31.1, 3, 5, 8, this is what they want you to do for every component and piping system. So it's pretty straightforward. And the test procedure is pretty straightforward. Here are the equations for the mean collapse of bends in straight pipe. So if you have something you need to do tonight and you have a hard time going to sleep, you can work through these equations and see that the allowable load that you're developing in Caesar is exactly 1/2 of the twice elastic slope load for straight pipe and bends, as long as you use I for bends. 0.75 I for bends is closer to the nuclear criteria. This is the interesting thing. You'll see a whole bunch of new things with the nonlinear calculations coming in the next 6 months from us, I think, and potentially from other people, because when you run a pressure calculation in ANSYS or our software or whatever, and you're doing an elastic analysis, if you take pressure right to the limit, you can't add any external loads to it, right? I mean, that's the problem. So you've designed it optimally to pressure, it doesn't carry any extra loads in the nozzle. Because a little bit of extra stress, the allowables are the same, so you're overstressed. In reality, what happens, these are 2 tests for collapse of a branch connection. So when we pressurized it, the allowable doubled. So the collapse capacity doubles due to pressure. So what's going to happen is as soon as you start running nonlinear analyses, you're going to see that behavior. And for certain thicknesses of pipe, that's very accepted. So what's going to happen now is you're going to have higher allowable loads for pressurized components. And people are going to wonder what happened. They're going to run elastic analysis, say you're way overstressed, and you're going to have to justify it. So here it is. We can talk about it. You will see it in our software within the next 6 months. It's supposed to be released last year. Had to redo the algorithms, blah, blah, but it's going to be released shortly. And then you'll hopefully be able to do this with ANSYS and other tools also. We do it automatically. Okay, the last thing, but not least, the new version of Caesar now includes a sustained load case for every operating case. That was B31.3 guidance in 2014. So you'll have a whole lot more sustained load cases than you ever had before running Caesar with B31.3. So you will have more sustained load failures. So then it will, pardon?
No, that's good.
Well, I think it emphasizes the fact that it is important to use the right sustained stress index, 0.755. That's going to be important. But it's also important to know when is a sustained stress overloaded? When is it really overloaded? And these slides, we don't have time to talk about them, but I'll give them to you. What happened, well, they'll be in the slides, right? So if you get this up. So what it basically says is that when you have liftoff, you can go through this evaluation for each location and decide if it should be overstressed or not. What's that based on? It's based on twice elastic slope. What's the twice elastic slope based on? Twice elastic slope is based on the concept that if you run an elastic analysis, you're overloaded, you have collapsed when your elastic analysis predicts 1 inch and you really get 2 inches. You get double what you calculate. So knowing that, we can go back and develop criteria for supports that lift off a little bit. Because a support that lifts off 0.001 inches isn't susceptible to collapse. And a support that hasn't lifted off at all in an elastic condition is certainly not going to collapse. So it's something interesting to think about, because at some point in your life in the back, but yeah, I know you've gone through, oh, is this really a sustained failure? Do I really have to stay late and reroute this pipe? Do I really need to talk to the client about this? Because you've had a sustained overstress. And you will probably see more. That was really not last but least. Really last but least is, well, I'll tell you what, this is bad. There's OLEDs that people are selling in the industry. What happened is somebody decided to make OLEDs cheaper. So instead of manufacturing them with double bevels, well, really triple bevels, they decided to come in and cut the contour in the opposite 90 degrees so they could fit it over the pipe easier. So what that does is it puts the longitudinal weld, the small weld, in the longitudinal plane rather than, well, it puts a small weld in the longitudinal plane, big weld in the circumferential plane, which is the opposite of what you want. So these things don't have anywhere near the weld capacity in the high stress area that you need for any kind of pressurized concrete. So we will be building some of these. We're having a manufacturer build some of these when we get back to Houston. We'll be pressure testing them and fatigue testing them. But what you see in FEA Tools now is you see an option for very poorly made OLEDs. So you can put that in and we generate what we think is a reasonable finite element model for that and give you very high I factors for these guys. So just be aware that you can buy junk on the internet that does not come close to satisfying what was the original intent of OLEDs. Last but really not least is this. I think you've seen some of that. I hope that in the future, whenever anybody does a retrofit of any kind of piping system or a new piping system, that you're very cognizant of the technology that's available with scanners today. Scanners have gotten so fast and so accurate that you can go out and scan an operating condition, put it into the FEA Tools software, tell it which Caesar models might match those deflections. The software goes out, reads the Caesar models, and then tells you which of the sustained cases to operating cases gives you the range that you see in the scanned results. We did that with a 2-inch piping system in Houston. So it was pouring down the rain outside our office. Here was the system. It was pouring down the rain, little system, right? We just wanted to build something that we could validate the scanner with. So it's got a stainless steel cap on it, it's got a stainless steel cone on it. So we had to run it through FEA Tools to get the flexibilities. So we slid a 1-inch block under it, and that was the initial displacement. So we wanted to see if the scanner would be able to detect that in terms of movement laterally in this length of pipe. So it moves it a little bit. So what we took all this, we did it here, it was no problem. With the scanner located right here, it was no problem. So I said, well, I mean, it's 5 feet away. Okay, well, okay, so it should be pretty accurate. I mean, it was almost no error. So then we took it outside in a rainstorm and moved it to the end of the parking lot, which was 250 feet away. So scanning through a rainstorm, it got the displacements of this accurate to within 1/10 of an inch. I mean, really, really amazing. So what I'm going to argue that you'll be able to do is you'll be able to take these scanners, and this plant was scanned, and this image was developed, the bird's eye view image was developed from those scanner locations taken on the ground. Each scanner location takes maybe 5 minutes to scan. 360, well, it scans 180 degrees because there's it's got two things on both sides. 180 degrees. So what it does is it lets you build bird's eye views. So you could take drone, essentially like flying a drone around the plant. And if any of you have ever worn Nomex and big heavy steel-toed shoes, boots, a hard hat, and carried all your equipment in a plant and climbed up to go look at supports and then got back down, driven back to the office and forgotten to take a measurement, you know, this solves that problem. You will never go into the plant again because once they do the scanning, you can go back and find where you left your glasses because the scans can find, they're that accurate and they're that detailed. They take photorealistic images. You see bird poop on the pipe, you see stripped insulation, you see left off bolts, you see hanger rods leaning, you see stops that aren't included in spring cans, and you can measure center lines of pipe. And then put those in the seizure model, or put those in FEA Tools. It compares them to the seizure model and tells you if you're close enough or not. Gives you a percentage error to the maximum displacement. So if the maximum displacement's an inch, it will tell you if the maximum error in your calculation is a percentage of an inch. So if your error is 100%, then you know you're off by an inch somewhere. You're predicting an inch of displacement or 0, where it's getting an inch of displacement or 0. I think I said that right. And so what happens is there will be critical systems where when you scan them and then compare them to the seizure results, they don't match. And so somebody guessed at a tower temperature for you that was just way off. Tower temperature wasn't anywhere near that hot. So the line only went up 1/4 of what the guy told you it would go up, which is typical. You want to know what the real thicknesses are. Nobody will ever have to ask what friction factor should I use again. Because you put in a variety of friction factors and a variety of seizure runs, it picks the one that's closest to where the actual displacements are. So you know exactly what friction factor to use. All these things are answered. So I think scanning, because it is so cheap and so accurate, will be a big part of your toolkit. I'm also going to argue it's going to be a big part of new design toolkits, because you will specify critical lines because we're going to be screening for them, because we're very sensitive to those now because they're costing us extra money. So we'll screen for new critical lines and new systems and then require that those are scanned. And then those are going to be validated. So your seizure calculations will actually be checked against something that's monitoring what's going on in the plant. And why do we do 5% X-ray? We do 5% X-ray not because it helps anything, because the welder knows he's going to be looked at. So as pipe stress engineers, we know somebody's going to go behind us and check us now in a very detailed way for critical lines. So we're just going to pay a little bit more attention. And my last comment would be, we run a lab in Houston. We've run the lab for probably 15 years, never had an accident. My insurance guy came to me and said, "Why are you spending so much money on safety?"
That's why.
That's why. You know, don't cut back on safety because you're safe. Right? There's too many things that change, too many things that happen. I mean, and that's what's going on in the plant. There's too many things that are happening. We need to do more to be safe, not the same amount. Thank you very much. I appreciate your attention.